If you look at the skull of a modern human alongside that of any other primate, the most striking difference is not just the vault of our brain case, but the extraordinary flatness of our face. Every chimpanzee, gorilla, and ancient hominin ancestor possesses a massive, projecting lower face, a forward jutting snout anchored by thick, heavy bone, and powered by colossal jaw muscles. Their skulls are biological engines built for raw power. They are designed to exert hundreds of pounds of bite force to crush fibrous roots, strip tough bark, and tear through raw, rubbery muscle tissue. By contrast, the modern human face looks strikingly delicate, almost fragile. Our jaws are small, light, and pulled back directly beneath our eyes. Our chin is a subtle protrusion on a shortened mandible. Our cheekbones are light, and our teeth are smaller relative to our body size than those of almost any other mammal of comparable weight. We possess no sagittal crest atop our heads to anchor massive chewing muscles, and our zygomatic arches, the bone structures that frame our cheeks, do not flare outward to accommodate giant pulsing temporalis muscles. For decades, evolutionary biologists treated the human face as a mere backdrop to the story of the human brain. The conventional narrative suggested that as our brains expanded, our skulls simply reshaped themselves to hold a larger central processor, but biomechanical research has revealed a far more surprising truth. Our faces did not shrink simply because our brains grew. Our faces shrank because we changed how we eat. Long before modern culinary culture existed, our ancestors made a fundamental technological leap that altered our biological trajectory. They began processing their food outside their bodies, first with stone tools and later with fire. Hominins transferred the grueling mechanical work of digestion from the mouth to the hands and the hearth. By tenderizing, slicing, pounding, and ultimately cooking their meals, early humans drastically reduced the physical force required to consume calories. This shift relieved the relentless evolutionary pressure that had maintained massive jaws and teeth for tens of millions of years. It triggered a cascade of anatomical shifts that transformed our skulls, reallocated our energy budgets, enabled the development of articulate human speech, and ultimately shaped the physical visage you see in the mirror today. But this evolutionary bargain also left us with a strange and painful paradox, a biological mismatch that leaves millions of modern humans struggling with crooked teeth, impacted wisdom teeth, and obstructed airways. To understand how cooking made us human, we must first look at the brutal mechanical reality of the world before the flame. 3 million years ago, in the woodland savannas of East Africa, hominins like Australopithecus afarensis lived in a world dictated by the physical toughness of raw food. Their diet consisted largely of underground storage organs, fibrous roots, tubers, and bulbs, along with tough seeds, nuts, wild fruits, and the occasional scavenged carcass. For a primate without cooking technology, eating raw plant material or unprocessed raw meat is an exhausting full-time job. Wild tubers are packed with tough cellulose and lignified fiber. Raw meat is elastic and rubbery, stubbornly resistant to being crushed by flat molars. To break these materials down so that stomach acids can extract nutrients, an animal must chew them incessantly. Chimpanzees today spend as much as 5 to 6 hours every single day simply chewing their food. The anatomy of Australopithecus reflected this relentless mechanical demand. Their cheek teeth, the premolars and molars, were enormous, covered in extraordinarily thick enamel. In fact, some species, such as Paranthropus boisei, evolved teeth so massive that paleoanthropologists famously dubbed them Nutcracker Man. These hominins possess deep, thick jawbones capable of absorbing enormous rotational strains without fracturing. To power these jaws, they had massive temporalis and masseter muscles that attached high up on the skull, creating a broad, flaring architecture across the midface. Every stroke of an Australopithecine jaw exerted immense pressure. When a creature chews tough, raw vegetation, the teeth do not merely crush, they grind back and forth under high force. This mechanical strain stimulates the bone cells in the growing jaw, causing the mandible and maxilla to expand and thicken. The bone builds itself up to withstand the forces imposed upon it, creating a wide dental arch with ample room for every tooth. In this raw world, a small jaw was a death sentence. A hominin with small teeth or weak jaw muscles could not process enough raw fibrous material in a day to meet its energetic needs. Natural selection ruthlessly favored heavy masticatory machinery. For millions of years, the primate face remained locked in this heavy-duty configuration. Yet, despite their massive jaws, Australopithecines were ecologically constrained. A large chewing apparatus requires significant metabolic energy to build and maintain, and the sheer amount of time required to chew raw food imposed a strict ceiling on daily caloric intake. They were spending vast amounts of energy simply converting raw matter into digestible pulp. Around 2.6 million years ago, a dramatic break occurred in the archaeological record. In regions such as Gona and Ledigararu in Ethiopia, hominins began intentionally flaking stone to create sharp-edged cobbles and stone blades, the Oldowan tool culture. For a long time, researchers assumed that cooking with fire was the sole trigger for the reduction of the human face. But recent experimental biomechanics has shown that a critical transformation happened long before humans mastered fire. That transformation was mechanical food processing. In 2016, evolutionary biologists Katie Zink and Daniel Lieberman at Harvard University published a landmark study in the journal Nature that investigated what happens when humans eat raw diets processed with primitive stone tools. Human teeth are not designed like those of carnivores. True carnivores, such as lions or wolves, have specialized blade-like teeth called carnassials that shear through raw flesh like scissors. Human molars, by contrast, are flat-topped grinding basins. When a human tries to chew raw, unprocessed meat, the flat molars simply flatten the elastic muscle fibers without breaking them apart. The meat remains in a single rubbery lump, making it nearly impossible to swallow or digest efficiently. Zink and Lieberman brought human volunteers into the laboratory and equipped them with electrodes to measure the electrical activity of their jaw muscles, as well as sensors to measure bite forces. They fed the volunteers raw, tough meat, specifically goat meat, which closely mirrors the tough, lean muscle tissue of wild game, as well as raw, fibrous root vegetables. The researchers tested 4 conditions: food that was completely unprocessed, food that was pounded with a stone, food that was sliced into smaller pieces, and food that was cooked. The results were astonishing. When volunteers ate raw goat meat without any mechanical processing, they could chew it hundreds of times without successfully breaking it into smaller particles. However, when the raw meat was simply sliced into bite-sized pieces using a basic stone flake, the number of chews required to prepare the food for swallowing dropped dramatically. Slicing raw meat reduced the required chewing force by 26% and cut the total chewing effort by nearly 17%. Pounding tough root vegetables with a stone cobble had a similar effect, breaking down tough plant fibers before they ever reached the mouth. Zink and Lieberman calculated that if early hominins like Homo erectus incorporated just 1/3 raw sliced meat into their diet alongside pounded plants, they would reduce their total chewing cycles by nearly 2.5 million chews every single year. This discovery provided a crucial missing link in human evolution. Slicing meat with basic stone tools relaxed the evolutionary selection pressure for giant cheek teeth and massive jaw muscles. It demonstrated that mechanical processing alone could initiate the flattening of the human face roughly 2 million years ago, laying the biomechanical foundation for the arrival of fire. While stone tools began the process of tenderizing the hominin diet, fire transformed it entirely. Cooking is not merely a method of heating food, it is a fundamental chemical transformation. When heat is applied to meat, it denatures the tightly wound collagen proteins that make muscle tissue tough and elastic, converting them into soft, water-soluble gelatin. When heat is applied to plant tubers, it gelatinizes starch granules, swelling and rupturing their rigid crystalline structures, and breaks down tough pectin and hemicellulose walls. This thermal breakdown does 2 things simultaneously. It makes food exponentially softer, and it vastly increases its caloric bioavailability. Cooking acts as an external digestive system. It performs the chemical work of breaking down complex molecules before the food ever enters the stomach or intestine. The precise timeline of when early humans mastered fire remains one of the most fiercely debated topics in paleoanthropology. Biological anthropologist Richard Wrangham has argued for the cooking hypothesis, proposing that Homo erectus mastered fire as early as 1.8 to 1.9 million years ago. Wrangham points out that the transition from Homo habilis to Homo erectus marks the most dramatic anatomical shift in human history. A sudden reduction in molar size, a shrinking of the gut, a a reduction in jaw size, and a massive 40 to 50% jump in brain volume. However, many field archaeologists urge caution. Unambiguous, widespread hearths and burned bones appear consistently in the archaeological record around 300,000 to 400,000 years ago, at sites such as Kesem Cave in Israel and Schöningen in Germany. Earlier evidence of fire exists, such as microscopic ash and burned bone at Wonderwerk Cave in South Africa, dating to approximately 1 million years ago, and burned seeds and flint at Gesher Benot Yaakov in Israel, dating to 780,000 years ago. But these early sites are rare and heavily debated. Whether thermal processing became ubiquitous 1.8 million years ago or grew incrementally over the last million years, its biological consequences were definitive. Once cooking became a regular part of hominin life, the physical demands on the human mouth collapsed. Food was no longer a tough, fibrous substance that required hours of violent grinding. It was soft, yielding, and densely packed with accessible calories. The heavy, thick jawbones that had defined our ancestors for millions of years were no longer an evolutionary advantage. In fact, they became a liability. Maintaining thick bone and giant chewing muscles requires metabolic energy. In the unyielding arithmetic of natural selection, any anatomical structure that consumes calories without providing a survival benefit is eventually selected against. As thermal processing rendered heavy jaws obsolete, individuals with smaller, lighter faces survived and reproduced just as effectively, if not better, than their heavy-jawed peers. The stage was set for a dramatic reshaping of the human skull. To understand how the face physically altered its architecture, we must look at the biomechanics of skull growth and muscle geometry. In a heavy chewing primate, the face is pulled forward away from the brain case, a condition known as prognathism. This forward projection serves a structural purpose. It creates a long lever arm for the jaw, allowing the temporalis and masseter muscles to generate massive crushing forces at the back molars. As food became softer through stone tool slicing and thermal cooking, the biomechanical forces acting on the skull changed. The temporalis muscle, which originates on the side of the brain case and attaches to the mandible, no longer needed to be thick and powerful. As the muscle shrank, it no longer exerted high strain on the top and sides of the skull, leading to the disappearance of the sagittal crest and the reduction of the heavy bone ridges above the eye sockets. At the same time, the mandible itself began to shorten. The row of cheek teeth compressed. Premolars and molars decreased in size by more than half compared to those of Australopithecus. As the jaw shortened, the entire lower face retracted. Instead of jutting forward like a snout, the mouth pulled backward, coming to rest directly beneath the front of the brain case. Paleoanthropologists call this flattened vertical facial profile orthognathism. This facial retraction triggered a profound reallocation of metabolic energy, a concept explained by the expensive tissue hypothesis, formulated by Leslie Aiello and Peter Wheeler in 1995. The human body operates on a strict energy budget. Brain tissue is metabolically expensive. It consumes roughly 20% of the body's energy, while accounting for only 2% of its mass. Gut tissue and muscle tissue are similarly expensive to maintain. Aiello and Wheeler demonstrated that to expand our energy-hungry brains without drastically increasing our overall metabolic rate, humans had to downsize another expensive organ system. That organ system was the gastrointestinal tract. Because cooked food is so easy to digest, humans no longer needed the massive elongated colons and complex stomachs required by apes to ferment raw plant matter. As our guts shrank, our rib cages shifted from the wide, funnel-shaped structure of Australopithecines to the narrow, barrel-shaped torso of modern humans. And right at the entrance of that digestive tract, the jaw, teeth, and chewing muscles underwent a parallel reduction. Cooking freed up the metabolic capital required to grow a 1,350 cubic centimeter brain. The transformation of the face did not merely alter how we looked or how we digested calories. It inadvertently unlocked one of the defining traits of our species: articulate speech. In most mammals, including chimpanzees, the tongue sits entirely inside a long horizontal oral cavity. The larynx, or voice box, is positioned high in the throat, connecting directly to the nasal passage. This architecture allows animals to swallow food and breathe simultaneously, but it severely limits the range of acoustic sounds they can produce. As the human face pulled backward and shortened, it altered the geometric proportions of the vocal tract. The oral cavity was compressed horizontally, forcing the back of the tongue down into the throat, or pharynx. This movement pushed the larynx lower down in the neck. This structural shift created a unique two-tube vocal tract with a roughly 1-to-1 proportion between the horizontal space in the mouth and the vertical space in the throat. Biomechanical modeling shows that this specific 1 one-to-one geometry is required to produce clear, acoustically distinct vowel sounds, such as the I, U, and A sounds found across human languages. Without a shortened face and a lowered larynx, the human vocal tract would lack the acoustic precision necessary for rapid, complex speech. Here we see a classic example of evolutionary exaptation. An anatomical structure selected for one function ultimately enables an entirely new capability. The shrinking of our jaws, driven by the softness of processed and cooked food, unintentionally created the physical instrument required for spoken human language. Our modern faces became instruments of communication not only through speech, but also through visual expression. With the reduction of heavy brow ridges and the flattening of the midface, our facial muscles became finer and more differentiated. We gained the ability to convey subtle emotional nuances, a raised eyebrow, a slight smirk, a flash of surprise, enhancing the complex social coordination that defined human societies. Yet this evolutionary triumph carried a hidden vulnerability, one that affects billions of people today. While our genetic evolution reduced the baseline size of our jaws over hundreds of thousands of years, a second, much faster process was at work: developmental plasticity. Bone is a dynamic, living tissue. During childhood and adolescence, jawbones do not grow solely according to a rigid genetic blueprint. They respond directly to mechanical strain. When a child chews tough, resistive foods, the forces generated by the chewing muscles create mechanical loads on the jawbones. These loads stimulate the periosteum, the membrane surrounding the bone, triggering bone deposition and causing the jaw to grow wider, longer, and stronger. For millions of years, even after the invention of cooking, human diets remained tough enough to stimulate significant jaw growth. Hunter-gatherer children chewed dried meats, wild roots, seeds, and coarsely ground grains, ensuring their jaws grew large enough to accommodate all 32 adult teeth, including the third molars, commonly known as wisdom teeth. The tipping point occurred very recently in our history, first with the agricultural revolution roughly 10,000 years ago, and dramatically escalated by the industrial food revolution over the past 2 centuries. With the advent of ultra-processed, highly refined foods, soft white bread, boiled canned vegetables, ground meats, and sugary purees, the mechanical strain on children's jaws plummeted to near zero. Biological anthropologist Daniel Lieberman and physical anthropologist Robert Corricini have documented this phenomenon across numerous populations transitioning to modern diets. When children grow up eating soft industrial foods, their jawbones do not receive the mechanical stimulation required to reach their full potential size. However, the size of our teeth is almost entirely determined by genetics. Our teeth do not shrink simply because we eat soft food. This creates a critical biological mismatch: genetically full-sized teeth attempting to fit into an epigenetically underdeveloped, stunted jawbone. The result is a modern epidemic of malocclusion. Teeth crowd together, twist, and overlap. Wisdom teeth, arriving last in late adolescence, find no remaining space in the shortened dental arch, becoming painfully impacted against the bone. Furthermore, narrow jaw development often leads to a high, narrow hard palate, encroaching on the nasal cavity and contributing to airway restriction, mouth breathing, and obstructive sleep apnea. The braces, wisdom tooth extractions, and palate expanders common in modern dentistry are direct consequences of a diet that has become far softer than our evolutionary biology ever anticipated. When you look into a mirror, you are not merely looking at a collection of features, you are looking at a living archive of human technology. Our flat faces, soft cheeks, delicate jaws, and prominent chins are physical monuments to an evolutionary path shaped by stone tools and fire. We are the only creatures on Earth that cook their food, and consequently, we are the only creatures on Earth whose survival depends on an external kitchen. By outsourcing the work of chewing and digestion to the stone blade and the hearth, our ancestors traded a brute mechanical power for mental capacity, articulate language, and social culture. We shed our massive jaws so that we might grow big brains. We shortened our faces so that we might speak. Our delicate faces are proof that culture is not separate from human biology. It is the very engine that sculpted our physical form.